Okay, welcome, everyone. You have a few diehards here. I see lots of people are embracing the online options. Welcome. So I'm going to start today just with a few announcements about upcoming disruptions. The college is closed next Monday and the Monday after. So we're going to be 2 weeks without a class on Monday. Next week is our exam on Thursday. So there will be no class on Monday, and then on Thursday you will have your first exam, and it will cover classes 1 through 4. If you have done all of your homework and looked at all of the lectures, you should be fine. I'll post some more information about the exam, but roughly you will have the entire class period to do it. So you will have 3 hours to do your exam. You will come here to do it in person. You will have the use of a computer. You can use your personal computer if you prefer. You can use pen and paper. It is open book. You can actually bring anything you want. The only thing that you're not allowed to do is communicate with other people during the exam. So you can't email with people. You also should not use the internet. You should bring your own materials and do the exam by yourself. You can use the textbook, you can use your notes, you can use the calculators and various things that we have given you. You can use all of that. And I should note that it is my intention that you should not be under time pressure during the exam. So 3 hours will be a relaxed period of time. It is plenty of time to do everything that you need. The exam will be administered on Blackboard. So you'll come in, you'll start, you'll see the exam on Blackboard, you'll see all of the questions, you'll be able to answer them on Blackboard as you work them out, enter your answers. At the end of the time, you will submit it, and I will grade it via Blackboard. You won't find out immediately after the exam what your grade is, because the grading that happens always has to be manually reviewed. Even some of them, they're entered with decimal places, and Blackboard can be finicky about how it grades those. So I always manually review everything before assigning grades. Are there any questions about next week or the exam? So that is next week, Thursday at 5 p.m. Yes?
You can post questions, like sample questions online?
I could, if there's an interest in sample questions.
I guess, like, cause I'm just curious, in terms of like knowledge or working things out, like it might be, or like, yeah, like you said, like the homework questions, I guess.
Yeah.
It'd be nice to get an idea of how best to prepare based on the questions.
Sure, I will be glad to post some sample questions. Typically, I base them on the homeworks and on questions that are in your open intro textbook. So if those two sources, and I focus on things that are done in class. So if you've seen it in the lectures, you've seen it on a homework, and you see problems in your textbook, there's a good chance that things like that will be in the exam, because I take things that we've covered in the lecture, that we've covered in the assignments, and then I often look into the book for just ideas for questions. So, but yeah, I'll be glad to post some sample questions to help you prepare. Any other questions? How about the folks online? Are you checking the online questions, Tony?
I got the late people. I got one to reply. Everything's working. Yeah.
Okay, great. All right, if there are no more questions about, yep.
This isn't about the exam, but
yep.
I know 2 weeks after next Monday, we also have that Monday off as well. Will there be a makeup class that Thursday, or?
No. That week is just gone. That's, yeah, part of the 12 meetings per semester. It just doesn't include that week. It's, since we started early, we still have enough classes without that week. And all of this is in the syllabus. So if you forget about it and just take a look at the syllabus is correct. Okay, so today I'm going to review a little bit of the properties of probability that we learned last class, because you're going to be applying them and using them in some different situations today. We're going to be applying them to two important distributions, the normal distribution and the binomial distribution. And this is all coming from your textbook in chapter 3. So you remember we started using Venn diagrams to represent probability, where we have random events with specific outcomes. The event is something specific and measurable, and we use the Venn diagram with circles to represent the probability of these events. So 2 events, 2 circles. Here's an example of having cancer and not having cancer. These are mutually exclusive events if you either have cancer or not, so we represent them with 2 non-overlapping circles. And that means that they're mutually exclusive. There's no probability of both of them happening. And in this case, the union of the probabilities of these 2 events, so using that U sign, the union of the probability of having cancer or not having cancer is just the sum of these 2 events, probability of having cancer plus the probability of not having cancer. So if each of these circles represented, the area of them represented the probability, then the total probability is just the sum of those 2 areas. And if these options are also exhaustive, which they are in this case, because you either have cancer or you don't, then they have to sum up to 1. So the union of these mutually exclusive and exhaustive events is 1, and the intersection is 0 because there's no overlap in them. On the other hand, non-exclusive events have some overlap between them. So this probability of the union, so here's an example, cancer and heart disease. It is possible to have both. So the left circle represents your probability of having cancer. The right circle represents your probability of having heart disease. And this middle, the intersection, represents the probability of having both cancer and heart disease. And the union, which would be all of this area, represents the probability of having either cancer or heart disease or both. So in this case, that union, the OR, is equal to the sum of the probabilities of these 2 events minus the probability of this intersection, because otherwise it's getting counted twice. This bit in the middle, this probability of having both cancer and heart disease, the intersection, is equal to the product of these 2 probabilities if the 2 are independent. If the conditional probability of having cancer if you have heart disease is the same as the conditional probability of having cancer if you don't have heart disease. But if they're not independent, then this conditional probability rule has to be calculated using a prior and the likelihood. And this was where we came up with Bayes' rule. So then the probability of having cancer and heart disease is the probability of cancer given that you have heart disease times the probability of having heart disease. Or conversely, the probability of having heart disease given you have cancer times the probability of having cancer. And you remember we wrote out those 2 ways of doing this conditional probability, and that's where Bayes' rule came from. Is that all still kind of clear in your minds? Just give you this little probability notation cheat sheet, but I won't go over it again today. But this would be a good thing to remember and to have with you during your exam, just saying. Yeah?
Is there an example of the probability you can think of, like in terms of the way you multiply across?
Mm-hmm.
From you multiply so you're multiplying Yeah, so let's say the probability of having cancer, that would be expressed as like a decimal. Is that the way you would express it?
Yep, the probability of
It's like,
having
say,
cancer would be.
0.10 or 0.1.
Mhm.
So,
Yep.
and then if the probability of having heart disease is 50%.
Yep.
So you just do 0.1 times 0.5.
Yep, that would be this middle one if those two probabilities are independent. And the reason that, and this simplifies from the bottom one, which is more general, in the case that the probability of having cancer, given that you have heart disease, is just the probability of having cancer because they're independent. If they're not independent, then you need to know this conditional probability.
Okay. Right, because it might change the value of how likely it is that you have second condition.
Right. So if having if having cancer is more likely, given that you have heart disease, which is probably true because they both tend to affect older people. They're not completely independent if you were to look at the entire population. If you have heart disease, you're probably older and you're more likely to have cancer as well. So then this conditional probability is not just equal to the probability of having cancer.
Could it
Yeah.
possibly go the other way?
Yep.
Like something like sickle cell anemia and malaria or whatever, like the odds of having the one actually drive down
Absolutely.
the likelihood of having the other.
Absolutely. Your conditional probability could be higher or lower than the so-called marginal probability, which is just the probability of having cancer regardless of whether or not you have heart disease, or your probability of getting malaria regardless of whether or not you have sickle cell anemia. But yes, it can go up or down. In fact, in this one, if we were to put in H-, not having heart disease, then it would go in the other direction. Yeah. But yes, I would like for you to be familiar with these basic rules of probability and to be able to do some basic calculations using them. So we used these a bit last week with diagnostic tests, and we're going to take it further this week by looking at random variables. And by random variable, I mean any characteristic that we can measure or categorize that has a definite outcome, but where at least part of that outcome is determined by chance. So just a few examples of random variables. The number of new diabetes cases in New York City in a given year. It's going to vary from year to year. It might depend on structural factors such as what people are eating, how old the population is. But part of it is going to be due to chance. At least we don't know what causes some of the fluctuations, and we would have to model that as being random. Or the weight of a randomly selected individual in New York City, also a random variable. So we might know that it depends on a few things systematically, like age, height, sex, if we knew those things, but at least part of it is going to be unpredictable, so we would model it as a random variable. You'll remember these types of random variables from the first class, the categorical random variable, discrete, and continuous random variables, with categorical including binary and multi-level categorical and ordinal. Just a bit of notation. We're going to write random variables in capital Roman letters, so capital X, capital Y, and particular realizations of those random variables in lowercase levels. So the distribution of heights in the population we might write as capital X, but then the heights of some individuals we would write as lowercase x1, x2, etc. Let's look at a couple more examples of random variables. So blood groups. What kind of random variable is this? Categorical. Very good. So so for any individual, their blood type is one of these. After we've measured it, you know, that's a realization of a random variable. It's a random variable when we don't know what it is. We know approximately what the probabilities of them are in the population. And every time we look at an individual, take a blood test, and determine their blood type, that's a realization of that categorical random variable. How about the number of visits to the obstetrician's office during an uncomplicated pregnancy? So this is if we look at the population of women who have had an uncomplicated pregnancy and count for any of them, for all of them, how many visits they had to the obstetrician. What is that? Continuous? I would call that discrete, just because it only takes on the integer values of 0, 1, 2, 3. It can't be 1.5 or 1.2. So this is a discrete quantitative variable. How about the distribution of body mass index in a population? Yeah, that's continuous. It can take any value. It can be fractional. It can be integers if you round it off, but it depends on height and weight, and it can take any decimal value, so it's a continuous variable. We will describe these continuous random variables. I'm going to start with them. We'll talk a bit later about categorical, at least binary random variables later. But for continuous random variables, we're going to describe them by their probability distribution. And this probability distribution can be plotted as follows, with the possible values that the random variable can take and a curve showing the probability of each of those variables, with the probability on the y-axis. And we're going to be, in general, not so much interested in the values along the y-axis here, but in areas under intervals along this curve. And that we will look at those areas to tell us the probability of making an observation within some range or interval of values of the random variable. And any interval along this curve must have a cumulative probability. It has to be greater than 0. So if it is a possible value that the continuous variable can take, it's the probability of observing it must be non-zero, but it can't be greater than 1. So general property of probabilities. And finally, the interval containing all of the possible values, of course, has to have an area that adds up to 1. So it's these areas that matter, and the areas are interpreted as probabilities. We're going to look today at continuous outcomes. We're going to consider the normal distribution. We'll talk about some other distributions later on in the course. Today, just the normal distribution, which is the bell-shaped curve. And for binary outcomes, we'll look at the binomial distribution. Starting with the normal distribution. And it is an important distribution, not only because many observations, many random variables that we observe in the real world are normally distributed, but it turns out that there are properties of samples that make any kind of observations, when we look at their average values over samples, look like a normal distribution. We'll get to that in a couple classes under the central limit theorem, but as a result of this, it is the most important distribution in statistics, and one that comes up for all kinds of data. Its key aspects are that it's symmetric, so it has a peak, and it is a mirror image on either side of that peak. It's sort of bell-shaped, and it's characterized by two and only two parameters, the mean and the standard deviation, with the mean being at its center and the standard deviation describing its spread. So here are just a few examples of, let's see, we have in red here, here is a mean of 0 and a squared standard deviation or a variance of 0.2. In green, you see some normal distribution with the same mean, but a larger standard deviation, so it has wider tails and a lower peak. And then in blue, again, a 0 mean and an even larger variance of 5. So lower peak yet and a very, very wide tails.
Those are normal distributions?
Sorry?
Are those all?
These are all normal distributions. Yep. Just normal distributions with different values. Here, it's only different values of the parameter sigma. And here, a different value of both sigma and mu. So this one has a mean of minus 0.2 and a standard deviation or a variance of 0.5. So it's just...
That's not criterion for calling it normal distribution. Or the mean just happens to be shifted down on whatever that scale is. So I guess that's not...
These are all normal distributions. Yeah, and I'm just trying to make the point here that the normal distribution has two parameters that change the distribution. So the shape of all of them is still this bell-shaped symmetric curve, but the center of it can be moved by changing the mean mu, and the spread of it can be changed with this parameter sigma. But they're all normal distributions. Those are the only two ways that you can change the normal distribution with mu and sigma, the mean and standard deviation. Just a couple more concrete examples. These are the heights of women with a mean of 65 inches and a standard deviation of 3.5 inches, and the mean and heights of men with a mean of 70 inches and standard deviation of 4 inches. So you see both this shift and the spread being a little bit different. And we have overlap in the two curves and a small area where there is not much overlap. So let's see, yeah, within what interval do almost all of the men's heights fall here? The men's.
65, 75.
58 to 82.
Yeah, 58 to 82. That's as far as we can see on the drawn line anyways. So that is, so 82 would be 3 standard deviations above, and 58 is 3 standard deviations below the mean. And for women, let's see, 65 up to 75, that's again about 3 standard deviations, and down to 55, that's again about 3 standard deviations. And it turns out there's a rule for that we call the empirical rule. We call it an empirical rule because it's, it's not, there's nothing special exactly about 1, 2, and 3 standard deviations. It's just kind of a convenient intervals to use. But it is useful, and it is a property of any normal distribution that if you go within plus or minus 1 standard deviation of the mean, there's a 68% probability of observations falling within that interval. 2 standard deviations, you're up to a 95% probability, and 3 standard deviations of the mean, it's a 99.7 probability. So like we noticed on that last slide, that almost all probability lies within plus or minus 3 standard deviations of the mean. That's the empirical rule, and it applies to any normal curve, any normal distribution. So going back to this example with the adult women, with the mean of 65 inches and standard deviation of 3.5 inches. That empirical rule tells us that 68% of them will fall within the mean plus or minus 1 standard deviation, which is 65 minus 3.5 and 65 plus 3.5. 95% within 2 standard deviations, and 99.7% within 3 standard deviations, which is 54.5 to 75.5 inches. And just looking back at these, that was 54.5 to 75.5. That's 99.7% of women's heights fall within that range. You can also use it for non-symmetric questions. So if you have the question of what proportion of women are less than 68.5 inches tall, well, 68.5, that was 1 standard deviation above the mean. So it is going to include this 68%, plus it is going to include what is to the left of 1 standard deviation. And since it was 68%, 16, and 16, we can just add those two and get 84%. And these little exercises, and you'll be doing more of them, they're handy just for getting you used to using probability distributions to estimate probabilities. And this is important not just for the exercises, but because it is with calculations like this that all of the hypothesis tests that you will learn in statistics come from. They come from counting the area under intervals of curves. In general, hypothesis tests, the way they go is that under a null distribution, we have a test statistic that we know what its probability distribution is. We look at a curve like this and calculate what the probability is of having a test statistic in a certain region. And then if that's a small probability and our test statistic is within that region, we reject the null hypotheses. So it is important to be comfortable with these probability distributions and to be able to make calculations with them. So we've seen a few different normal distributions with different means and different standard deviations, and all of those are normal distributions. Any of them can be standardized. You standardize a normal distribution by subtracting the mean and dividing by the standard deviation so that you end up with a mean 0 and a standard deviation of 1. And this is called the standard normal curve. And there's only one of those. It has a mean of 0 and a standard deviation of 1. So the equation for converting a normal distribution x with standard deviation mu and, with mean mu and standard deviation sigma is this, and it gives you a new random variable called capital Z that is the standard normal distribution. When we transform actual observations taken from a normal distribution using this transformation, those are called z-scores. It's called a z-transformation into z-scores. Unless you're north of the border, then they're z-scores, which is what I used to call them. But I've gotten used to z-scores now. So there are many different normal distributions. There's just one standard normal distribution. And you remember that the normal distributions I plotted, they look kind of different in terms of their location and their width. Well, actually, they all look the same except for the scale on them. So if you just adjust the height of the y-axis and move the x-axis and scale them, they look exactly the same. So that compression is an artifact of the difference in the x-axis and the height of the y-axis. So here's an example with the normal distribution of heart rates and beats per minute with a mean of 60 and a standard deviation of about 20. After converting it to a z-score, the mean is 0 and the standard deviation is 1. So sorry, the standard deviation would have been about 10. Once it's been converted to the standard normal, the standard deviation is 1, but the curves look the same. A good reason to use the standard normal distribution is because there's only one of them. It makes it easier to look up probabilities. So whereas with the normal distribution, you have a different distribution for every value of mu and sigma. There's just one standard normal distribution. So you can look up probability values in a table in the back of your book, and you can immediately interpret these z-transformed z-scores. And in your textbook, in Appendix B.1, there's a normal probability table that gives you probability values for different z-scores along the standard normal distribution. And it gives you this nice plot like this, showing you that the intervals are to the left of the value of z that you are looking up. So for negative z, this is maybe z of minus 0.1, you'll see some value between 0 and 1. It's a probability, and it is the area under the left tail of this curve. And if you see positive values of z, it'll be something. So here, this probability is less than 0.5, right? And here for positive z, if this is, say, 1, it'll be something greater than 0.5, and obviously still less than 1. And it points out this useful property to you from, you remember, for the mutually exclusive events, that the total area 1 is equal to the sum of the probabilities to the left and to the right of any point in the curve. So if you need a probability to the right of a particular value of z, what it's suggesting to you is that you look up this value to the left in the table and then go 1 minus that to get what there is the probability to the right of that value of z. So here's what that table looks like. Maybe before showing that, I just wanted to give you an example of looking up a probability in here. It's a little bit hard to see, and you're going to get some more practice with this later anyways. But if we wanted the probability that a normal random variable takes a value of mu plus 1.43 standard deviations or less than that, we would look up in this table the probability for a z-score of 1.43. So we would go down the column here and find 1.4, go across to 1.43, and we see something there that looks like 0.9236, if I read that correctly. And if we wanted the probability to the right, so of a value greater than 1.43 above standard deviations above the mean, it would just be 1 minus that value, or 0.0764. Any questions? There are a few important z values. Probably the only one that you really should remember, and that you will remember by the end, is this one here, this probability of a z-score greater than 1.96, so just under one tail, is 0.025. And that one's important because if you look at both tails, so the probability of z greater than 1.96 or less than minus 1.96, it is 0.05, which is a common probability used for hypothesis tests and for confidence intervals. So you'll be used to this value of 1.96. These other ones are good if you wanted to construct hypothesis tests at other significance levels or confidence intervals other than the 95% confidence interval.
So is this saying that the odds that a given score is greater than 1.96 on that x-axis, or 1.96 standard deviations. I guess one is equal to one standard deviation, right?
Yeah, so I don't have the whole table here, but it's saying that if we looked up minus 1.96, the probability to the left of that is 0.025.
Same for the right.
And the same for the right. So the probability above 1.96 is 0.025. The only one this table would have is the minus, well, it would have the minus 1.96 as 0.025, and under the positive z part, it would have, under 1.96, it would be a probability of 0.975. The 3 decimal places. So the area to the left of z equals 1.96 is 97.5%. Is there another question? Oh. How are we for time? We're okay for time. So let's do another exercise here then. What is the probability that a normal random variable assumes a value within 1.43 standard deviations of mu? So this is the middle part within plus or minus 1.43 standard deviations. So between a z-score of minus 1.43 and 1.43. And we already looked up on this page that the probability of a z-score less than 1.43 is 0.9236, but that includes all of the area to the left. So here we don't want to count this part under the left tail, so it's going to be something less than that. There are a couple of ways we could do this. One is to take this entire area to the left of 1.43 and then subtract the amount to the left of minus 1.43. And this part we have, it is 0.9236. And this part, the probability of z less than minus 1.43, is the same as the probability of z being greater than minus 1.43 minus the probability of z being less than 1.43. The probability of z greater than minus 1.43, which would be all of this, minus this tail.
Which is what's greater than, which is past 1.43.
Yep, yep. So this solution here, the way you could look this up in the table would be the probability of the probability under 1.43. That's going to give you 0.9236 minus the probability to the left of z equals minus 1.43, which is going to give you 0.0764. If we could read this table, that would be, well, we don't have any negative values here, but it would be 1 minus 0.9236. So 0.9236 minus 0.0764 gives us 0.8472.
That there being an 84.7% chance.
Yep. Yeah, 84.7% chance of having an observation between minus 1.43 and positive 1.43 standard deviations from the mean. An alternative way to do this, either way works just as well, is to start with the total area 1 and then subtract twice the area under this left tail, which is 0.0764, and that gives you exactly the same answer. So my suggestion, and you will be solving some problems like this when you're asked to calculate probabilities under various intervals, under various probability distributions, is in general, go ahead and draw out that curve and shade the area that you want. And this can be helpful even when doing hypothesis tests, especially if you get into one-tailed hypothesis tests, which we don't emphasize too much. But there are cases where you will do a one-sided hypothesis test, and it's important to make sure that you're calculating the correct probability. And the best way to do that is to actually draw it out and shade the area of probability that you want, such as here, and then start writing in various probabilities until you can get exactly the area that you want. So in this example of calculating probability to the left of z equals minus 0.64, let's see, different example than here, but I'm just talking about filling in these various areas under the curve to make it easy to simplify it down to some arithmetic after you've looked up your correct values. So this is one use of that table, or of the Excel function norm.dist, or there's a function in SPSS as well where you look up a certain value of z and get the probability. But you can do it in the other direction as well, where you want to know under which part of the curve contains a certain amount of the probability. And we do that by looking at the table in reverse, or in software using the so-called quantile function. So before it was a probability function, this is called a quantile function. So for example, if you wanted to know under what central area of the normal curve contains 84 or 85% of the curve, you could calculate, you would know that you wanted 7.6% or 0.0764 under each of these tails. And by looking up the 0.0764 quantile, you would find that that was a z-score of minus 1.43. So the reverse use of the table is called the quantile function. So if we were going in the other direction, and rather than me asking you, okay, what is the probability of having an observation outside of 1.96 standard deviations from the mean, and instead asked you how many standard deviations from the mean will you find 95% of your observations in a normal distribution, that would be a quantile lookup or a reverse table lookup, where you, in the table in the back of your book, you would look for a probability of 0.025, and you would find a value of z of minus 1.96. So just to give you a nice step-by-step process of the whole problem, you'll start by stating the problem in terms of the random variable in the capital letter and your observation in the lower level, such as you want to calculate the probability of the random variable, so the probability of this random distribution being less than a particular observation in lowercase. You'll standardize x to restate this problem in terms of the z distribution. Draw a picture to show what probability you're calculating, and then go ahead and calculate that area using the standard normal curve in the appendix of your book or using software. All right, we have a bit of time now to introduce you to the binomial distribution. You will use the binomial distribution in cases of a binomial variable, so one where it can take only two different possible values. For example, having cancer, not having cancer, having private health insurance or not having private health insurance. So if you have only one observation, binomial distribution isn't very useful. It is useful for describing repeated observations of this binary variable. There are three conditions under which you can use the binomial distribution. So the first one is that every trial has two possible outcomes, and we call these successes and failure, even if that doesn't necessarily make a lot of sense in the context of the problem, such as having private health insurance or not, having cancer or not. Those aren't exactly successes or failures, but just in terms of thinking about the binomial distribution, it helps to think of one of the outcomes as the success, and that is the one that you count. It's the one where you want to count the number of times that it occurred. So first condition, that the trial has two possible outcomes. Second condition, that each one of those trials has the same probability of success. So if I'm talking about having private health insurance, a priori, as far as we know, everyone who we're going to ask whether they have private health insurance has the same probability. So this is a requirement for describing the outcome of the number of people who, in this sample of some size, have private health insurance using a binomial distribution. At a later point, you will get to doing logistic regression, and you'll learn that you can through a regression model different probabilities for each one of those individuals depending on covariates or other measurements about them, so that they don't all have the same probability. But to model a single event or outcome as the number of successes using a binomial distribution, every one of those observations or each trial has to have the same probability of success. And finally, these N trials, so a trial being each person who we ask what kind of health insurance they all have to be independent. So if I'm going along, the probability of the fourth person I ask having private health insurance has to be independent of what the third person said, what the second person said, what the first person said. They're just each independent trials. Like when you roll the dice, what you roll one time has no impact on what you roll the next time, as long as they are fair dice and they're not being manipulated somehow. So if these three conditions hold, then the probability of success given N trials, so N being, in the example of private health insurance, the number of people who we ask the type of health insurance, the probability of X successes, so out of those N people, how many of them have private health insurance, where each one has a probability of success or of private health insurance of P, then we can describe this entire distribution of the probability of each number of outcomes. So if we have 100 people, we can calculate the probability of everywhere between 0 and 100 of them answering yes using this distribution. So every possible value between 0 and n has a non-zero probability, and it is calculated with this formula, where this is the factorial and factorial, and this is the probability to the power of the number of successes and n minus x. These are some actual plots of binomial distributions. There are 3 of them I've put on here. Let's take a look first. This red one, this is n equals 20. So say 20 people with a probability of success for each one of 0.5. So what is the most likely number of successes if you have 20 people and a probability of success of 0.5? You have 20 people, you have a probability of your outcome of 0.5. What's the most likely number of successes, the number of yeses? 10. Yeah, so you see this peak here at 10, and you see it dropping off on either side of 10, so that your probability of 0 successes or of 20 successes is quite low. Going up to n equals 100, so 100 people with a probability of 0.5, what's the most likely outcome? Yep, 50. You notice any other difference compared to this red distribution? So it's shifted to the right. Notice any other difference between this normal distribution on the left and the one on the right?
More gradual.
Yeah, it's wider, right? Has a greater variance. So, you know, whereas this one we could only see values going up to, you know, maybe 7 or 8 plus above and below the mean. Here it's more like 15 above and below the mean. And one more for 100 individuals, but a probability of success of 0.3. It's the most likely number of successes. 100 people, each has a probability of success of 0.3. 30, yeah. And that's what we see here, the mean at 30, and some spread on either side. You notice anything about these curves? How would you describe them? Yeah, they look kind of normal, right? This especially looks normal. You can see here, down here, maybe it's a little, well, it looks pretty normal down there too. Maybe it's a little bit more asymmetric for this one on the left. But yeah, they look kind of like normal curves. And it turns out that they are pretty well approximated by normal curves. We'll cover that. So using that formula, you can do it in a spreadsheet. I'll give you a calculator that has a spreadsheet that's already calculated for doing this, but there's also a binomial probability calculator built into Excel. But here's an example. So let's say the prevalence of diabetes in an elderly population is 10%. We're going to call having diabetes a success here. So again, there's no judgment in the use of the word success here. It's just statistical terminology for these trials, which we call Bernoulli trials. A success is whatever it is we're counting. So in this case, success is having diabetes. What is the probability then if you randomly select 4 individuals from this population that exactly 3 of them will be diabetic? You can just plug this directly into that formula that we had. The probability of x equals 3 when n equals 4, and a probability of 0.1 comes out to be 0.0036. If I were to do this for x equals 0, 1, 2, 3, 4, and add them up, do you know what I would get? 1, right. That's right, it's a discrete probability distribution. The probability is non-zero only for integers, and the only possible values for a trial of size 4 is an outcome of between 0 and 4. So if I calculate those 5 probabilities and sum them, I have to get 1. And you can ask all sorts of questions. This is pretty well analogous to the calculations we were doing on the normal curve, but with a discrete distribution what's the probability that if you randomly select 4 individuals from this population that at most one of them will be diabetic? Well, we can calculate it for x equals 0 and x equals 1 and just add them up. So it's an interval, but along a discrete distribution. How about the probability that if you randomly select 4 individuals from the population that at least one of them will be diabetic? So 1, 2, 3, or 4. The easier way to do this is, rather than calculating it for x equals 1, 2, 3, 4, is just to calculate it for x equals 0, and then calculate 1 minus what you get for probability of x equals 0. And that x equals 0 was 0.6561, so it's just 1 minus that, about 0.34. So that's all fine for small values of n, but if you get into large values of n, calculating the exact binomial distribution becomes problematic because of those factorials in them. So if you have several hundred, a trial of size, let's say 500, 500 factorial is a really large number, and it might cause an overflow on the computer. And what you can do, and what the software is going to do anyways for very large values of n, is to use this normal approximation that you noticed on that plot before of the exact binomial distribution. The approximation is that the mean, as you noted on that plot, the mean is going to be the number of trials times the probability of success of each trial. So when we had n equals 100 and a probability of 0.5, the mean was 50. And a standard deviation that is the square root of this n times the probability times 1 minus the probability. And so this accounts for how you notice that those higher probabilities also had greater variance. This is how you can calculate what that variance or standard deviation is for different values of n and p. And this is especially useful for large samples. So if you have an n of 1,000, then you can estimate the prevalence of, and you know the probability of having diabetes as being 10%, then if you were asked a question about what is the probability of sampling between, I don't know, 10, having in this sample between 10 and 50 individuals with diabetes, you can answer it using this normal approximation. This works especially well for reasonably large values of n and p, and just as a rule of thumb, if both np, which is your expected number of successes, and n times 1 minus p, which is your expected number of failures, if both of those are at least 15, then the normal approximation is going to be very, very good. It's still not bad if it's less than that, but it's very, very good if you're above that threshold. And just as an example here of calculating your probability of between 5 and 8 successes on a binomial distribution, it would be this discrete sum of 4 values, whereas if you were going to use this normal approximation, it would be the probability of x. You go halfway in between and calculate your probability of a x between 4.5 and 8.5. Yep.
Does that mean that before we use normal approximation, we need to test n times p? n times 1 minus p before we even go into
It's
that?
a rule of thumb. So, you know, that binomial distribution is a little more asymmetric and not quite normal if either np or n times 1 minus p are less than 15. So so yes, if those are small, then it's not so bad to use the exact binomial calculation as opposed to the normal approximation. All right, and here's just a summary of the things that we covered today that you should remember. The probability notation and calculations are important both for the stuff we did in the last class and today's class. We're going to be using these two distributions, the normal distribution and the binomial distribution, throughout the class. We covered a little bit of new notation, the upper and lower case x for random variables and particular instances or realizations of the random variable, n for the number of trials in a Bernoulli trial, where there are two outcomes, and p for the probability of success in each. I guess mu and sigma you knew already, but we covered the capital Z, the standard normal distribution. You should, by the end of today, and by the end of the lab, be familiar with probability calculations and lookups using both the binomial and the normal distributions, and be confident with calculating probabilities under upper, lower tails, or in the middle of a normal distribution. All right, thank you. Are there any questions before we say goodbye for the lecture, take a 10-minute break, and start the lab? All right. Thank you.
Okay, guys, take a walk.